Ebbinghaus's 1885 forgetting curve showed that within 24 hours, humans forget approximately 70% of newly learned information. Within 1 week, 90% is gone, unless the information is reviewed. This research, nearly 140 years old, remains the most replicated finding in memory science. Yet the way most people study, reading once, highlighting, and reviewing the night before, is precisely the approach that maximizes forgetting. The neuroscience of memory consolidation identifies 4 specific techniques that dramatically change retention rates: spaced repetition, retrieval practice, interleaving, and sleep-driven consolidation. Roediger and Karpik's 2006 psychological science paper, Test-Enhanced Learning, provided one of the most counterintuitive and consequential findings in educational psychology. Testing yourself on material you have studied produces 50 to 80% better long-term retention than rereading the same material the same number of times. The act of retrieval itself strengthens the memory trace, a mechanism Roediger called the testing effect. This video draws from 5 peer-reviewed studies across psychological science, neuron, memory, and cognition, and the foundational 1885 experimental psychology work by Ebbinghaus, covering the forgetting curve, testing effect, spaced repetition, sleep-driven consolidation, and desirable difficulties. The dominant study strategies taught in schools, rereading, highlighting, summarizing, and mass practice, cramming, are the strategies that research consistently shows to produce the least long-term retention. They create a feeling of fluency, familiarity-based, without building the durable memory traces that produce actual recall. Bjork's research on desirable difficulties showed that techniques that feel harder in the moment, retrieval, spacing, interleaving, produce dramatically better long-term retention than techniques that feel easy. Walker and Stickgold's 2004 Neuron Review established sleep as an active memory consolidation process, not merely a passive rest period. During slow-wave sleep, hippocampal replay of recently acquired information transfers episodic memories to neocortical long-term storage. During REM sleep, procedural and conceptual memories are consolidated and integrated with existing knowledge networks. Missing sleep after learning produces forgetting rates equivalent to not having slept at all. The contrast between ineffective and effective study strategies can be summarized by the principle of active versus passive encoding. Passive encoding, rereading, creates familiarity but not recall. Active encoding, retrieval, generation, testing, builds the associative networks that allow information to be accessed under varied conditions. Roediger and Karpik's 2006 experiment directly compared study strategies in undergraduate students learning scientific texts. The testing versus study design showed that 3 testing sessions without rereading produced significantly better 1-week retention than 3 rereading sessions, despite lower performance on immediate recall tests, demonstrating that the difficulty of retrieval was building memory strength. Ebbinghaus's forgetting curve data showed that without any review, retention drops to approximately 58% after 20 minutes, 44% after 1 hour, and 26% after 1 day. But a single review at 20 minutes resets the curve, with subsequent forgetting occurring at a shallower rate. This is the mathematical basis for the spaced repetition algorithm used in tools like Anki. Memory research has produced a clear ranking of study techniques by their effect on long-term retention. This ranking, integrating Bjork's desirable difficulties framework and Roediger's testing research, is now well established in cognitive psychology. Memory formation is a biological process requiring multiple stages: encoding, consolidation, and retrieval. Each stage has specific requirements and vulnerabilities. Understanding this mechanism reveals why certain study techniques work and others fail at the cellular level. The evidence-based learning optimization framework implements 4 techniques simultaneously: spaced repetition, active retrieval, sleep consolidation, and interleaving, to maximize long-term retention of any type of information. Implementing a memory optimization protocol produces measurable changes in retention on a timeline that aligns with the memory consolidation biology, from immediate encoding improvements to long-term durable memory formation. The daily implementation of a memory-optimized learning protocol requires 6 consistent practices that transform how information is acquired, consolidated, and retrieved. Memory optimization strategy must be personalized based on the type of information being learned. Procedural skills, conceptual understanding, and factual recall require different emphases within the framework. The neuroscience of memory provides a clear answer to how to remember more of what you learn. It requires active techniques that feel harder, not passive review that feels easy. Here is what the research shows. The evidence is clear. The mechanisms are understood. And the techniques to remember more of what you learn are within reach for anyone willing to trade passive review for active retrieval. Follow MedBrief Today for more science-backed health insights, explained clearly.